Hey everyone, Elmo here. Back at it again with another upload. Today we're going to be talking about Bessel functions and the various intriguing properties associated with them. In this video, we'll actually lead up into a video about Hankel transforms and how to evaluate definite integrals with Hankel transforms. So stay tuned for that. And for starters, there are going to be two different Bessel equations. There's going to be the regular one and the modified one. And so we'll start off with the regular one. The regular equation is going to produce two different functions as its solution. So that's going to be Bessel function of the first kind, j sub v, and Bessel function of the second kind, y sub v. And so both obviously pretty oscillatory. And so another property associated with both of them is how they, or a property associated with all Bessel functions is how they react with being near zero. So at zero, j sub v is going to, as you increase the order of v, j sub v at zero, around zero, is going to be zero. Or it's going to be really small, except for except for v equals 0. Now y sub v is going to be the exact opposite. Well, not exact opposite, but it's going to be the opposite. So y sub v, it's going to, as you increase the order of v around 0, there's going to be an increasing vertical asymptote. So just x, as you let x equal 0 and v equal anything, or anything large, or no, anything, this function will go to minus infinity. It's gonna fall all the way down there in that vertical asymptote. So, next up are a few properties. The first one is absolutely indispensable. Well, all of these are pretty indispensable, but this one's really, it's really fundamental. So the first property is going to be this derivative property, and so with the derivative property, it makes it so you can integrate. This makes it so you can integrate so many different products of Bessel functions with variable ease, and so the next one is going to be the basic property. Oh, by the way, you see the notation here, c sub v? C sub v of x, it just means Bessel j sub v of x or Bessel y sub v of x. So the properties are going to be identical for both of them in this case. So, so that's the basic derivative property, and this is the recurrence relationship. Makes it so we can simplify expressions that are pretty cumbersome. And this one, at any time you have a negative order, you can just put -1 to the. So it's going to be both an odd function and an even function, but it's going to be based on the order. So if you have an odd integer order, it's going to be an odd function. If you have an even integer order, it's going to be an even function. So now for complex input. So j sub v, or these both, if you put an imaginary unit in there with an integer x, or no, not integer x. X could be anything real. So, or x could be anything for that matter. If you put in any value for x with an I next to it, then you produce the Bessel functions or the modified Bessel functions. So for j, it's going to be I, and then for y, it's going to be k and I. But here are the general expressions and also the simplified ones that you'll probably see these a lot more. Now, time for the modified equation. So the modified ones are kind of like hyperbolic Bessel functions. So they're going to be very similar to their counterparts. So j sub v, remember how it was 0? As you increase the order, it's going to be 0 at 0 or nearing some small values, well, I sub v acts the exact same, except it's very similar to cosh. So if you let v equal 0, then it resembles cosh. It gets really divergent. However, k sub v, it's nearly the opposite once again, just like the regular equation. So k sub v, as you increase the value for v, you'll begin to see that this asymptote gets really intractable. Like all this area up here, the function's at infinity up here for like k sub 3 of x, as you can see. And so it's really unwieldy. That's why you're probably going to deal with k sub 0 of x. K sub naught of x is a lot more common and a lot nicer to deal with. But in general, Bessel functions are pretty hard to deal with. Okay, so is that everything? Yeah, that's about everything. Or actually, k sub v is going to be very convergent at infinity. So it nearly outconverges, or it does outconverge an exponential at infinity. So, okay, next up, once again, some basic properties. So z sub v, that means any modified Bessel function. And so you have a very similar derivative definition, except instead of a minus sign right here, it's a plus sign. And then right here, you have the same exact derivative property. And the recurrence relationship, except once again, except right here, it's going to be a minus sign instead of a plus sign. And for any order, for any negative order, it's just going to be a positive order. So it's going to be even for the order, an even function of the order. So, and now, for the complex input, we have basically the same thing. We just saw this, and right here. But right here, it's basically the same thing once again. So, except this equation right here is really, really valuable. And this equation, the bottom one, is so valuable that it has its own function named after it. That's called the Hankel function, which has next to nothing to do with the Hankel transform. It's used to actually prove the Plancherel's theorem, but it's invaluable nonetheless. So, okay, we'll talk about the Hankel transform in the next video. Like, subscribe, comment, share with your friends. Hope I was able to tickle your brain today, and maybe you tickled mine. And yeah, have a good one.